So this is the recording for 9.8 for honors geometry. The lesson is about applying other angle relationships in circles. I know this has been maybe a tough week. Sorry guys, it's not great. I know doing these lessons on video, but just kind of do the best you can, keep up with it, and please email me or send me remind text to, if anything I can help you with. Alright, so we're going to start with a quick warm-up because it'll be a good way to see if you understood 9.7, which was yesterday's inscribed angles, and then from there we'll move into the new stuff. Okay, so some of this I already worked out, but let's walk through this together. So when I see a diagram like this, I know that this circle here has none of the angles really were filled in except for the 50-degree angle, but when I see this, you can tell that this angle here, where the A is, if I draw that angle out, it's opening up to this inscribed, or the intercepted arc, this entire thing. This is a semicircle when it goes through the diameter like that with BC. So we know that this 180 degrees of the intercepted arc has to be cut in half to get to the inscribed angle right here. So that's where I got this 90-degree angle from, because it's got to be half of the 180, which I got from it being a semicircle. So if you need some work to kind of understand where that comes from, that's right here, where we know that the measure of arc BC is 180 because it's a semicircle. And then the measure of angle BAC, which you really could just call angle A even, is going to be half of the arc that it's opening up to, the intercepted arc, which is arc BC. And we know arc BC is 180, so that's where we get 90 degrees. Now, you don't have to show all this work if you don't want to, but that's kind of where it comes from. So far, we know this triangle is a right triangle now because it has that 90-degree angle. Then you want to figure out the other angle, because it's going to be a 40 degrees because this was 50. That means that this triangle cannot be an isosceles right triangle. It has to be a scalene right triangle. Cannot be equilateral. There's no such thing when you're dealing with right triangles. So because the angles were not the same, base angles have to be the same in an isosceles right triangle. So that's a nice little kind of application of inscribed angles, something you saw yesterday. Just make sure you're familiar going between inscribed angles and their intercepted arcs. Alright, so then we came to the next part, and it's just kind of filling in the different angle measures for the same diagram. So it says find the angle and the arc measures for measure of angle CAB. We found that to be 90 degrees. The measure of angle ACB would be 40 degrees, because we just figured out from a triangle, we know the 50 and the 90, you can just subtract from 180 to get 40. The measure of arc CAB, make sure you go to the letters in order, that would be this whole right hand side. That's also a semicircle. So although CB is a semicircle, so is CAB. And so that would be 180 degrees. And finally, arc AB, because I know that this arc is the angle that opens up to it is angle ACB, which was 40 degrees, I have to double it to get to this arc, because it's the intercepted arc for this inscribed angle. So double 40 to get to 80, that is the answer for arc AB. Okay, so that's how we get all those missing arcs and angles and arc measures. Now the last question is kind of an application of some trig that we had already done in the past units. This is not going to be on a quiz or a test, but it's good practice for the final exam for sure. So when I see the same diagram, but now it's asking me to find the side lengths. Well, what I do know is that the radius is 5.6. But in my diagram here, the only radius would be going from point to the center. So like that's saying this is 5.6 and this is 5.6. So if you want to either add them up or double them, that gives us 11.2 for segment BC. So that is the hypotenuse, that's BC. So now I start looking at my diagram. I labeled it BAC like this, and I know my hypotenuse is 11.2. I also know some of the angles, but let's say I only put in this angle here, the 50-degree angle. I could use sine, cosine, or tangent to help me find the missing side lengths, because I am missing both side lengths, or I could find one using sine, cosine, tangent, and then use Pythagorean theorem. So I did do sine and cosine on this. I did sine of 50, so ignore that 11.2 for a second, but sine of 50 would be opposite over hypotenuse, x over 11.2. Then I wanted to multiply by 11.2 to cancel it out there, multiply it on the other side, so that you can figure out what 11.2 sine 50 is in your calculator, and it comes out to 8.6. So that is the length of segment AC. This is AC. Okay, so once you know that measurement, you can either use Pythagorean theorem now, or you can do it one more time. You could say a cosine of 50, because it's using this side now, the angle, and then the side closest, the adjacent side is y over 11.2, and then multiply by 11.2, and you found out that you would type that into your calculator, 11.2 cosine of 50, it comes out to 7.2, and that would be AB. Okay, so we found both those sides. We already knew the hypotenuse from the beginning was 11.2 for BC, so that's all three sides. All right, so again, don't worry too much about something like this. It's just an application of the same idea with just kind of using some trig. But let's move on to the new stuff now. And so we're going to look at the 9.8 practice, or the notes actually first, and then we'll get to the practice. So at the top here, it's talking about applying other angle relationships in circles. So we've seen a little bit with some relationships with circles so far. We saw some things with tangents last unit. We've seen so far yesterday, we saw stuff with inscribed angles. We've seen some different descriptions of different lines and their the theorems that we covered, specifically the theorems from the last unit. Now there's some more theorems, and so it says if two lines intersect a circle, their intersection it's either going to be a vertex or it's going to be like the intersection of two lines. Sometimes the vertex of the angles form, like if you imagine two lines meeting, they form an angle that has a vertex to it. And it can be on the circle, inside the circle, or outside the circle. So those are the three choices or three options. Either on it, inside it, or outside it. And so for each one of those different scenarios, there's a formula that can be come up with to help you figure out some of the different angle measures. So it says the formula for the measure of the angle is dependent upon the location of the vertex of the angle. So depending on is it on, inside, or outside, these different scenarios will look slightly different. There are going to be some similarities and then some differences with the formulas. You do need to memorize these formulas. That's the only way you will know how to do these. These will not be provided to you. You have to actually memorize them. Okay, and so the nice thing is we have already done this theorem 10.7 yesterday, so it's kind of a recap here because this is an example where the vertex is on the circle. So it took two lines, but when they intersected, they met at the actual on the circle, not inside of it, not outside of it. We're going to see all those scenarios today, but these first two examples you see at the top here are going to be when the vertex is on the circle. Okay, so let's look at the first one just to kind of recap. So I wrote down here that this is an example of inscribed angle, or you can also mention intercepted arc. Those are the two things that we see in this diagram. This right here is the inscribed angle, angle C, or ACB, and then angle or arc AB is the intercepted arc. So just to kind of recap from yesterday, when you write down the equation or the formula here, it's the measure of angle C is equal to 1/2 the measure of arc AB. Okay, so this is the arc AB, and it's opening up to this inscribed angle. That's why it is the measure of angle C is equal to 1/2 measure of arc AB. All right, so that's it for the first one. And again, this is just a recap, but just kind of reminding you that all formulas of this kind, they're going to always look like this when you have a vertex on the circle. And so here's another example. Vertex is still on the circle, but this time, if you notice that what's in the diagram here, it's not these two lines specifically have names to them that we've learned. The first one up here is a tangent line, right? ED. Here, line ED is a tangent line, and chord, this is a chord here, CB or BC, is a chord because it's just 2 points on the circle connected. So I like to call this, it helps to have like a little mnemonic device here. I like to call these different theorems just kind of a way to help me remember them. It might help you as well. So I call this one chord and tangent because it literally has a chord and a tangent. Instead of trying to remember the theorem numbers, like, oh, this is theorem 10.11 or theorem 10. Whatever, it's easier just to kind of memorize it with the little description. Okay, so here's what this description says. It's still on the circle. So it's got to have this exact same formula. But let's look at how it applies here because the diagram looks a little different. So I did label angles inside here, angle 1 and angle 2, just kind of right next to each other. So what happens is when you have a tangent and a chord that connect or intersect, they're going to form like to the circle. And so when that happens, angle 1 here is opening up to this arc. This is arc CB. And angle 2 is opening up to the other arc. So what we can write down here is that the measure of angle 1 is equal to 1/2 again, because notice how it's still the same formula, and we want the measure of the arc that it's opening up to, in this case CB. Okay, that's all we would do on this one. Now we can technically write down an equation for, or like the second formula if you wanted to, for measure of angle 2. I didn't do that because there's not 3 letters here, but technically if you were to add a letter here, you could write down C, whatever this letter is, and then B, because it would be the same format. So just remember, whenever I see 2 lines that intersect on the circle, it's always going to be 1/2 of that arc that it's kind of like opening up to. In this case, it's called like an intercepted arc. You could technically still call this an intercepted arc. It just looks a little different. So look for the angle and the arc that's kind of creating that angle, and it's always going to be 1/2 of the arc. Okay, so that's what happens when it's on the circle. Let's see for the next 2 scenarios. Theorem 10.12 says vertex is now inside the circle. So I named this one crossing chords. This is nothing official. This is just like a mnemonic device to help remember them. Okay, so the reason I called it crossing chords is because you have 2 chords that cross one another. They will meet like inside the circle. That's why it's saying inside. So now this formula looks different from the other 2, right? Because it's no longer on the circle, it's inside of it. So here's what ends up happening. We have some angles here. Let's look at only one angle at a time. Let's look at angle 1 first. Angle 1, and obviously its angle that is across from it is a vertical angle. These 2 angles are the same, but let's look at the arcs that are created from them. This is an arc DC, and we have arc AB. Okay, so what we end up doing here is, this is the relationship. Measure of angle 1 is equal to 1/2 of arc AB plus the measure of arc CD. So it takes both of those arcs and it adds them together, and then remember the 1/2 is still there. So the nice thing about all of these different formulas you're going to see today is that all of them have that 1/2. So it kind of makes it a little easier to not have to remember so many different details. But basically, idea here is just add up both of those arcs that are across from that angle. Same thing happens with measure of angle 2. It would be 1/2 of the measure of arc BC plus AD. Okay, so that's it for theorem 10.12. And finally, the last theorem, it says vertex is on the outside of the circle. So there is, this one I've named kind of external angles of 2 lines. If that's too long, just call it external angles. But it basically is something we've seen before. We saw these external angles when we were working with tangent lines, specifically this one here, where we saw a circle, 2 tangent lines that kind of meet outside the circle. We talked about how these 2 segments were congruent. This was back from one of the theorems that was in the last week. But now we're going to learn a little bit, something a little different. So the main formula looks like this, where it's still got the 1/2. It still has, well, the angle would be equal to it. So you could say angle, I don't know, whatever angle it's referring to, would equal what this is. But it's saying outer arc minus inner arc. So what that means is the outer arc and the inner arc that create that external angle is what you are subtracting. And you always take the bigger one, which is the outer, and subtract the inner one, which is the smaller one. So this one in this diagram would be measure of angle 1 equals 1/2 again, and then you want to subtract the outer, which is JK, measure of arc JK, minus the measure of arc LM. That's it for that one. And again, it's just the idea that